Hi, welcome back to the YouTube channel. If you don't already know, my name is Amok Abdul and I'm a college math instructor. And in today's video, we're going to look at how to find the volume of a solid shape under the function and over a rectangle, right? And this is an overly simplified case. There are cases where we don't have rectangle and we have different sorts of regions. But let's just look at this simple case and see how we can solve this problem. And then in our solution, we're going to use two methods. The first is we use purely Riemann sum to evaluate this. And each rectangle we are going to use will be of area of 4. So we have to find this region and find the smaller rectangles. And then we'll solve the problem using double integral. So let's just get started. Now in using Riemann sum, so what we have to do to approximate this is we don't care. So we could, if you like, you could actually draw the shape, the solid shape that you would like to find the volume of, but this is not necessary in this case. All we need to know is to know our region first. We need to know our region and we need to know how to divide this region into smaller rectangles of area of 4. So let's just show our XY region. So this is the XY region, right? And then we have, so let me use a different pen. So we have the x-axis is between the x values would be moving between 2 to 10. So let's say this is 2 to 10, right? And the y, so let me use another color. The y will be between 2 to what? 8. Okay. Now, what will be this rectangular region? In the x, it will be this region, right? Covered by this red and white and green colors, right? So this is the region we are looking at, okay? Now, over this region, we have to now find a smaller rectangle. So we have to subdivide this into units of 2. Remember, we are asked to find smaller rectangles of units of area of 4. Now, the smaller the area that we have for each smaller rectangle, that would determine so that will determine how close our approximation of this particular volume will be. Okay, so let's just take a look at how we can first of all do this with area of 4. So in our mind, how we're thinking about this problem is on the x-axis, we are going to subdivide into into unit length of 2, so that we can get we can have unit squares. So basically, we're looking at unit squares where the length is 2 and the breadth is 2, so that the area of that square will be 4, right? So this would be 4. So this will be 6. Let's say this will be 8, and then we have 10. So this is not drawn to scale, so don't beat me up for that. So, and then on the right, on the y-axis again, we subdivide this into units of 2. So we have this. So this will be 4, this will be 6, and that will be 8. And here we have the same thing. So we would have these rectangles. And if you count correctly, we would have 12 rectangles. Now, actually, these rectangles are actually squares where the length and breadth are 2 each. Okay. All right. So now that we have this, we know that the area of each of any of this is actually 4. So which gives us the fact that what we have this under the bag. So we achieved an area of what? 4. Okay. Now you'll be thinking, why am I putting all these dots? I will explain in a bit. Now the Riemann sum says basically we should sum each strip which contains a base of where the base of this strip is this rectangle, and the height of that strip depends on the function 1 plus xy. Okay, so when you multiply base area times height, remember that will give you the volume, right? So this is how we are using Riemann sum to approximate this. So the volume will be the summation of all the volumes of those strip coming from each of these smaller rectangular region. Okay, so what does this mean? Now, the height will be determined by a point inside of this, or inside of each smaller rectangle. So let's call this X star, Y star. Then we'll multiply this by the what? The area, right, of each of the strip. Now note that, remember that what the area is actually of each strip is 4, so it's actually the same for all of them. So which means we can actually bring the area out, and all we need to do is multiply this area with the summation of the functional evaluation at these X and Y points. And these X and Y points are chosen from, these XY points are chosen from inside of this rectangle, which I'm putting as dot. So we are going to choose the midpoint, the point that is at the middle of each of this rectangle. So this is called the midpoint method. All right, so let's figure out these points. So for this first rectangle, so let me just show you with a different color. For this first rectangle, what would be this point? This point would be the midway through is 3, and the midway through is also 3 here. So that will give us 3, 3. So basically, area is 4. We got that. Now we are going to go on figuring out the sum of these functions at those points. Now, what does that mean? The first one would be at what? 3, 3. Okay, because the area times this times this height. So this is the height, which is determined by that point. F of this would determine the height of that strip. So when we multiply that by the area, it will give us the volume. So think of this strip as you have, think of each strip as this. So think of it as this cuboid, right? Where the height of this cuboid is determined by what? F of, so let's say in this case, F of 3, 3, and this base is determined by what? So this is the height, this point will determine the height, and then in each of this you have 2, 2, right? And this is how we're going to look at each strip coming out of each of this smaller rectangular region. All right, so this will give us the volume of this particular strip. Then we add it to all the other strips. So the next one will be the height of the next rectangle would be determined by this point, which is what? Half of it here, the X point is 5 and the Y point is still 3. So that will be 5, 3. We continue this way. The next one would be 7, 3. The next one would be 9, 3. Okay, then we are done with this row. We move to the next row. In the next row, for this particular strip, so for this particular region, what do we have? F of what? Remember the area is still 4 again, so it's 4 times height. And what will be the height now? F of 3, you can see when you trace by is 3, X is 3, and Y is what? 5. So we are having 3, 5. Then the next one would be what? The X is changing, 5, and Y is still the same, 5. The next one, which is this next one, that will be X is 7 and Y is what? Y is still 5. Okay, so let's just move it down. What about the next one? This last one would be F would be what? 9, X will be 9, and Y will be 5. Okay, then we move to the upper one, the last layer. In the last layer, we can see that what? X is still 3, Y has now become 7, right? Check. Y is now 7. Okay, so we have X is 3, Y is what? 7. The next one, X is 5. The next one, X is 5, Y is still 7. The next one, X is 7, Y is still 7. So I'm here now. So here, X is 7, as you can see, and Y is still 7. And finally, the last one, X is 9, and Y is 7. So this is the sum that we are talking about. So this sum, this Riemann, this is called the Riemann sum. This sum would approximate the volume of the region, I mean, of this function, I mean, the volume of this function under the region of this rectangle, right? That's what it does. So we just simply need to calculate this. Now, let me show you how the calculation works. So this is the function. So this is the function of xy that we have, okay? So let's come back to this. Now, f33 would be given as what? 1 plus 3 times 3, which is just 10. So f53, for example, will be 1 plus what? 5 times 3, which is 16. So that is how we are going to determine all of this, right? As an example, I just give you an example. So this would be, the first one would be 10, the second one would be 16, third one would be 7 times 3, 21 plus 1, that's 22. The next one will be 27 plus 1, that is, 27 plus 1, that's 28. The next one will be 16. The next one will be 26. F of 75 will be 36. F of 95 is 46. F of 37 again is 22. F of 57 is 36. F of 77 is 50. And F of 97 is 64. So we need to just add this together, multiply by 4. And it happens that what that gives you 1488. So make sure you go through the calculation yourself. So this is the approximate volume of this of the solid under the function and over the rectangle. Okay, right. So now let's look at the second method using double integral. Now the double integral is just calculating the limit when the area of each strip goes to 0. Okay, that's what it means. So where does the double integral comes from? So when we take the limit of the Riemann sum, when this area goes to 0, the sum of this function at this special points, dA. Okay, so when the area gets very small, what happens? The approximation gets better, and this turns out to be so I'm using just one sum, but actually it's double sum over x and y. Okay, so this becomes the double integral where x is moving between has a lower and upper bound, which is between a and b, and y is moving between c and d of this rectangle, right? Then we have f of what? xy dx dy. Now this gives us dA, okay, which is the area of the region, right? And another way to say this is the double integral over the region of x and y, that means over the rectangle, which is the region, then dA. Both of them are the same, so these are equivalent. Okay, so we're going to use this because we know the boundary of x. X was given between 2 and 10, and y was given between 2 and 8, right? This is what these boundaries are. So a is 2, b is 10, c is 2, d is 10, and d is 8. Okay, now let's calculate this double integral. So 210, 28. What is the function? F of xy is 1 plus what? Xy, then dx dy. Now this will give us the exact area of the exact volume of the shape of the solid that we're talking about, that we approximated using the Riemann sum. So now let's evaluate this. So first of all, we need to take the integral. We need to focus on this first. Take the integral of this function with respect to x. So let's do that first. So first of all, we need to look at this dx. Turns out that what integral of 1 with respect to x is just x. Think about this as if you are integrating polynomials. So the second term would be y is a constant, so we'll just increase the power of x by 1 and divide it by that power. And then we have to now evaluate this at what? X equal to 10, x equal to 2. So this gives us what? Evaluate this at 10, that will be y squared, which is 100 over 2y, minus, when x is 2, I have 2 plus 2y. Now, how did I get 2y? 2 here, that is x squared, which is 2 squared over 2, which is 4 over 2, which is 2. Now, when we evaluate this, I have 10 minus 2 plus 50y minus 2y. So that gives me 8 plus 48y. Now, this is the evaluation of this integral. So when I bring it back here, this becomes 2, 8. The integral of the inside, we already got it as what? Integral of 8 plus 48y. Now, what do we have left? dy. So now we are left with what? Integrating this. 2, 8, 8 plus 48y dy. Now, what does this give us? Integrate with respect to y. That will be 8y plus 48y squared over 2. Now we have to evaluate this at what? X, y equal to 8 and y equal to 2. Now, what does this give us? This gives us 8 times 8 plus 24 times 8 square minus, when y is 2, 8 times 2 plus 24 2 square. So how did I get 24? 48 divided by 2 is 24. Now, when I estimate this, this would give us 1,600 minus, when we evaluate this, you have 112. Okay, so this part is 1,600. This part is what? 112. And this final answer will give us 1,488. Okay, so this will be the volume of that solid, right, using double integral. As you can see, the Riemann sum did a very good job, right, in approximating this. So 1,488 is the same thing, right? So that means having a rectangle, a rectangle of which an area of 4 is more than enough to approximate this particular volume to its right precision. Okay, so this is the end of the video. If you like this video, give it like, give it the like button. Make sure you put on the bell button so that any new video that comes out, you'll be the first to know about it, and then for you to take a watch, right? So I would see you guys in the next video.